All right, good morning, pre-calculus. So I thought I would do a number of examples in polar coordinates just to kind of help and see if a few more examples might help out in helping, in you being able to follow something and actually get, you know, part of this to go out. Okay, so let me go ahead and share my screen, and we'll go ahead and try that. Okay, now these aren't out of a book. I'm just making these up as we're going. Okay. And I'm going to do this. Okay, so effectively, I'm just trying to give you some practice and like looking at some of the other polar coordinates that we have here. So try something like r is equal to, let's go with 4 minus 4 cosine theta. Okay, so on step 1 here, we're going to make, this is what I mean by, this is an r theta Cartesian graph. Okay, I'm still using Cartesian coordinates, except that the x-axis is now the theta axis, and the y-axis is now the r-axis. Okay, but it's still a rectangular graph. I'm just using that to kind of get an idea of what's going on there. Okay. Before I draw my graph, what I should have done was figure out, like, well, the biggest thing that cosine is going to be is is one. Cosine of 0 would be 1. 4 minus 4 would be 0. And then what are we going to be doing after that? It's going to be 4. If we have a negative 1, it's going to be 4 plus 4. That's going to be 4 plus 4 would be 8. So effectively, this graph is going to go from 0 to 8. So I'm going to go ahead and modify what I'm doing here. Okay. Just to get a plan of like where I think my graph is going to be, so I don't have to squish things in. And this is not a requirement for the class, but it is something. If you do this before you start making a graph, okay, a lot of your teachers are going to look at that and say, "Oh, wow, this person must really know what they're doing." Okay, so we're gonna give them the benefit of the doubt and things. Okay, so here's my r is equal to 4. 6, 7, 8. Okay. So here's my thing there. We're going to go from 0 to 2 pi. Okay. Pi over 2 and 3 pi over 2. Okay, so we'll do the easy ones first, right? When 0. When the theta is pi over 2, okay, the cosine of pi over 2, that's 0. So 4 minus 0, that's going to be up here 4. And 3 pi over 2, cosine of 3 pi over 2 is going to be, again, 0. And then 4 minus 0 is going to be up here. Okay. Now, if I put in, right, my 0 here, so cosine of 0 would be 1. 4 minus 4 times 1. 4 minus 1. 4 minus 4 is going to be 0. Same thing's going to happen over here at 2 pi. Okay. And if I put in a pi, right, the cosine of pi is negative 1. So this is going to be 4 negative 1 times 4 here, then 4 plus 4. So we're going to go up to 8. Okay, so we're going to be up here somewhere. Right. So units are all positive, thank goodness. Okay, so I don't have to loop around anything or think about things backwards. Just kind of figure that out. Okay, the graph, right, r cosine theta, it's equal to 0, right? R equals 0 when theta is equal to 0 and 2 pi. We can easily see that off of the graph, so that's not that big of a deal. Okay, and yeah, then we're just going to go ahead and figure out how to graph this thing in polar now. Okay, so as I'm going down here and I'm looking at it as a polar coordinate, actually we are going to have to go all the way up to 8, so I'm going to do the same thing. I'm going to make this a little bit lower. Okay. And again, theta here would be 0. Okay. Ooh, wait a minute. Nope, I'm wrong. Because where is it? At 8. It's at pi. So pi is going to be all the way over here. This. Okay. And again, I'm just trying to figure out like where I want to be at certain places. Okay, so here is my 0. I normally don't think this far ahead about things. So if this is theta is equal to 0, theta is equal to pi over 2, that's at 90 degrees. Theta is equal to pi, and theta is equal to 3 pi over 2. You can add in some additional points here if you'd like to, that's fine. But yeah, for the most part, here's what we have. Okay, now, when theta is equal to 0, then r is also equal to 0. Okay, now as theta as the angle sweeps, okay, the angle's sweeping from 0 to 90 degrees, what is happening to r? R is moving up to 4. So when theta hits pi over 2, my r is going to be 1, 2, 3, 4. All right. And then once we go from pi over 2 to pi, right, here's what's happening. We're going from 4 all the way out to 8. Okay, so I'm going to try to get this to be about and for those of you who are going into engineering, you know, the few times I've had, the few classes I've had, what I've noticed is that my engineering teachers were always delighted to pretend that matches up. Always delighted when you use like a straight edge, or actually you have to do your engineering homework on graph paper type stuff. Okay, I still can't get it. Don't worry about it. But if you're 3, 4, 5 triangles, 3, 4, 5, which is a very common homework problem in engineering classes, if that is the case, and you're trying, you know, your little structures work out to be 3, 4, 5 things, your engineering teachers are delighted by the fact that your graph is actually kind of accurate. All right, they really are. They really love it when you use a straight edge to draw your stuff. So if you're going into engineering, I'd recommend get a straight edge. Okay. For the longest time I was using my my Home Despot credit card for it. So, and then we're going to end up doing something like this. Okay, for 3 pi over 2 down to 0. So fourth quadrant, okay, we're going to start it down here, and then we're going to get progressively shorter until we get in here. Okay, and this is, you don't have to name these. Okay, you don't have to name them. That's fine. And if your drawings are half as good as mine, that's a really low bar. Okay, I think my graphs look like a third grader drew them. Actually, third graders probably do a better job than I would. But if you're that good, you're fine. Okay. But yeah, if you are in engineering classes and you want to, you have to draw straight lines, they love the fact that you would use a straight edge to do it. Okay. So that's one. That's 4 minus 4 cosine theta. Okay. How about we do a 5? We do a -5. No, that's going to be. I try not to do that too much, but okay, we'll just do a +5, but we'll do a +2. Again, we'll use cosine again. We'll use sine on the next one. We'll use cosine again. So we've got 5 plus 2 cosine theta. Okay, again, cosine of 0 is going to be 1. So 5 plus 2 would be 7. And at pi, right, cosine is -1. So it would be 5 minus 2. That would be 3. So my graph is going to run from 3 to 7, based around 5. Okay. So if I'm going to go ahead and graph my points here. Okay, again, here's theta. This is my our theta coordinate system. Okay, I'll put in Cartesian because I'm not graphing polar just yet. Okay. And then we're going to go from 3 to 7. So we're going to go here. Here will be 7. Do 1, 2, 3, 4, 5, 6, 7. Okay. Cheated a little bit, but there we go. 1, 2, 3, 4, 5. Okay, this is my R is equal to 5, right? Because that's just a vertical shift. All right, just a vertical shift. All right, so let's see here. All right, so again, we have to graph a cosine here. Okay, so here is 2 pi, here is pi, here is pi over 2, and here is 3 pi over 2, right? So graphing this, when theta is equal to 0, right? Cosine is 1, so we have 5 plus 2 would be 7. When we get pi over 2, right, we get 0, right? Cosine of pi over 2 is 0, so we just get 5. Cosine at 3 pi over 2 is also 0, so we just get 5. Okay. 2 pi would be back up here at 7. Okay. I know this is a terror. Give myself way too much credit for being on the level of a third grader here. Okay, and when it's pi, right, we get 2, but times -1, so we get -2. 5 minus 2 would be 3. So 1, 2, 3. All right, so here's our cosine. All right, pretend those match up. All right, so then we have to graph this thing on polar coordinates. So we have to go to 7 at 0 and 2 pi. 3 at there, and we're going to be at 5 up and down. Okay, so what was my 7? Yeah, okay. So we're a little bit exaggerated in this direction. Okay, and then we need to go up to 7. So this is theta is equal to 0. Theta is equal to pi over 2. Theta is equal to pi. Theta is equal to 3 pi over 2. All right. So when theta is equal to 0, this whole function r is equal to 5. No, is equal to 7. So we have 1, 2, 3, 4, 5, 6, 7. Okay, here we go. Okay. Now it sweeps up to 5 when we get to pi over 2, right? So as my angle is moving from 0 to pi over 2, the r is getting a little bit smaller. Okay, so 1, 2, 3, 4, 5. So we're going to go from here to here. All right. All right. Now, we get the pi, we're going to be down here at 3. Okay, so 1, 2, 3. So as I'm moving from pi over 2, right, as the angle is sweeping from pi over 2 down to pi, right, this whole function is getting a little bit shorter. We're going from 5 down to 3. Okay, so here we go. There we go. That's sort of. I know. It's like, are you sure third grade, maybe pre-K somewhere? All right. For the angle going down, right, we're going from pi to 3 pi over 2, and it's getting bigger from going from 3 up to 5. Okay, so 1, 2, 3, 4, 5. So right, so it's not going to be a circle. Okay, it's just not a circle. There is a little dimple in here, but since these are really far away from each other, the dimple is more pronounced when 5 and 2, when the A and the B get closer together. Okay, we're going to go back up to 5. Okay, sorry, 1, 2, 3, 4, 5 at 3 pi over 2, and then we're going to grow back up to 7. So it's almost circular, but not quite. Okay, it's still a lemicon, but the little dimple that we have there, it's a very small. Okay, it's a very slight dimple. I probably exaggerated it too much here. Okay, but this would be r equals 5 plus 2 cosine theta. Okay, you want to make them the 5 and the 2 very close together, right? This number and this number. So if I did like 10 plus 9 cosine theta, there would be a much more pronounced value. Okay, much more pronounced dimple when we do that. All right, so be on the lookout for that. Okay, but there we have it. Okay, so 3, right, is going to be, how about we do instead of that one, why don't we do something like 1 plus 2 sine theta? Okay, 1 plus 2 sine theta. So again, that way we'll have something a little bit more pronounced here. So when sine is pi over 2, we get 1 plus 2, which would be 3. When sine is 3 pi over 2, that's going to be negative, right? So we have 1 minus 2, that's going to go from negative 1. Okay, so we'll do something like this. All right, so we have 0 to 2 pi. Here's pi. Here is a pi over 2 and a 3 pi over 2. Okay, so this is just a vertical shift. Okay, here's r is equal to 1. Okay, so when theta is equal to 0, right, sine of 0 is 0. So it will be 2 times 0, which is 0 plus 1. When we have pi over 2, right, we get sine of pi over 2 is 1. So we have 1 plus 2 would be 2, 3. Right? We go over to pi, we're still going to get 1 here as well. And then 3 pi over 2, right, that's negative. So we go from 1 minus 2, that's going to be negative 1. Excuse me. So we're going to end up with a curve like this. Right? And one of the questions I'm going to have if it does this is, where the heck does it cross 0? Right? So what we're going to do is we're going to say 2 sine theta is equal to negative 1. We're just pushing the 1 on the other side. Sine theta is equal to negative 1/2. This is a nice problem. Okay. It's a very nice problem because this is one that you know, right? Theta equals sine inverse of negative 1/2. What value is that, right? Well, that's going to be a pi over 6, or at least a relative of pi over 6. Okay, so it's either going to be here or there, right? Or this is going to be negative pi over 6. But since we're looking at positive angles, this is going to be 11 pi over 6. And this is pi over 6 beyond the horizontal. Okay, so this was pi. We're going to go 30 degrees more, so that's going to be 7 pi over 6. I hope that helps a little bit. Okay, so it crosses it at 7 pi over 6 and 11 pi over 6. 11 pi is a hard number to write. Okay, so now we're going to go to polar coordinates. Okay, what are we looking at here? We're looking at a negative 1 all the way up to a 3. I think I have enough room to go ahead and do that. So again, theta equals 0 or 2 pi. This is pi over 2, pi, 3 pi over 2. Okay. So when theta equals 0, we are at r is equal to 1. Right? Now, when we go to theta, right, pi over 2, we're going to go from 0 to pi over 2. This is going to increase from 1 to 3. Okay, so we're going to have 1, 2, 3. All right. Now, we're going to go from pi over 2 down to pi, okay? And that value is going to return to 1. Try that. That's a little bit better. All right, now, when we get to 7 pi over 6 here, right? That would be 7 pi over 6. That's going to be about there for an angle. My value is going to end up doing something like this, right? And kind of curve into the origin at 7 pi over 6. Now, when we get to 3 pi over 2 here, okay, it's -1. So we would think it's going to be down here. We have to think about it like it's backwards. So we're actually going to be up here because it's negative. Okay, so we're going to end up with something like that. Okay, and then between 3 pi over 2 to 11 pi over 6, right, it's still negative. So we think we'd be in the 4th quadrant, but it's actually going to flip and we're going to be in the 2nd quadrant. And it's going to come back down around. So this is going to be, just say pretend that's 30 degrees. It doesn't look like it, I know. So we'll do it this way. Trying to mirror that. That's 11 pi over 6. Okay, so it's coming out like this. And then we just go back up to 1. Okay, it should be symmetric. Right, that's terrible. Okay, make this a little bit bigger, I guess, too, to make it have the same little loops that the other side does. And so it should be a symmetric graph. Okay, but that's how you graph this. I think this is the lemma escape. Okay, so that's what we have for how to graph these things. Right now, there are others. Right, if we have say it's just we have theta equals angle. Right? Let's do pi over 4. It doesn't really matter what r is. We're just going to have that. Just going to have that. Okay. Your homework does a pretty good job of like giving you lines to graph and circles to graph, but it does not do a very good job in giving us, you know, these types of graphs. Okay. Now, so yeah, there we go. When I took trigonometry back in the 20th century, in 1900s, we didn't have fancy programs like Desmos to do this. So most of my trig class was spent graphing because they said, well, you're not going to have a technology to do this for you. So we had to get really good at this. This was a thing. So we're just keeping it to the basics. Okay, we just have these 3 graphs, right? And that's pretty much what I want you to do and be able to do. Because when you get to calculus, when you get to Calc 2, you're going to have to do things like find the area, find this area. So you're going to have to be able to put that together to get this area here. Okay, and yes, you're going to be able to use your graphing calculators in that class. Okay, but sometimes, you know, remembering how to set it up and do everything is kind of, it's harder to remember how to do the calculator rather than be able to sketch it out. And I got to say, one of the saddest things I ever heard from one of the saddest things I ever heard coming from a student was they went to the Tutoring Center for Statistics. For those of you who are taking stats or have taken it, it's a lot of calculator work. And the poor tutor was there. It's like, I can't remember how to use my calculator to be able to get this answer, which is fair, but it's very sad that a tutor couldn't help somebody because they They're like, I completely forgot how to use my calculator. I'm like, could you at least, I mean, do you remember approximately where the buttons were? Do you know what you're looking for? Could you sketch out the problem? Something. So when you get to Calc 2 and they say, go ahead, we're going to use polar coordinates, and you have to be able to get the area here, having a plan of how to do this, of like, oh, let me graph it in a way that's easy first, translate it to this weird thing, and then sketch in the area you're actually looking for. You have to figure out like what angles you're going to be dealing with. Okay, so I want to know like from here up to there, kind of a thing. That's a whole piece that you have to do, and it's not saying you have to make the most accurate. Clearly, you don't have to make an accurate sketch, okay? But being able to make some kind of a sketch or have some place to go to start is an important thing. Okay, so if you're stuck and like, I can't remember how to use the calculator, well, can you do something? Okay, please. So that's kind of why we're doing this and pressing this on you. And if they're going to be more complicated, I would not, I would not say that using the calculator would be off limits, right? But they're usually going to tell you, it's going to be more complicated. But most calc problems I've seen, like really, actually the hardest ones are going to be something like sine of 3 theta. Okay, that's one of the hardest ones. That deserves its own video. That's actually, it's not a hard problem, but it is a long problem. Okay, and trying to figure out, like, find the area of one leaf or one petal. Okay, and then when sometimes you get like sine 3 theta. It's one of my, like this one. They'll probably do something like something like that, and trying to figure out like what's the area of like one petal. Okay, it's like a horrible gross. Okay, Desmos would do a much better job, but I would at least be able to say like, well, I know it's going to be from here to there. Okay, we're going to be okay. Or take the whole thing and divide it by 3. That might be a way to go too. Yeah, but when they put like a circle in here as well, and they'll say something like, get the area that's outside of the circle put inside the petals. Again, that's a very typical problem for a Calc 2 kind of a thing. All right, so just understand that's about the level. That's a hard problem. Not hard, but I mean this is above an average problem for Calc 2. Okay, so you'll get better. They'll teach you some techniques. You'll understand. Okay, I'm going to stop talking and let this go. But try to practice these types of problems. Okay, they really are kind of neat. Okay, so good luck. Try a couple. Practice.